You should start, Madhukar.
Yeah, yes, sir.
So I'll start recording once you see. I've already made you a co-host.
Yeah. I'll start sharing my screen. The slides are visible, I presume.
Yes.
Yeah, so we were looking at this problem of verifying RNNs using, of course, the technique that these guys propose uses invariant inference. Of course, this is invariant inference is in general quite a broad area in program verification. And so this paper does not talk much about invariant inference. These guys try to suggest that you can use invariant inference, and appropriately so, because recurrent neural networks have this some kind of a loop that we were seeing the last time. So in fact, this is how a simple example would look like. And so I'll recap some of what I covered the last time, and then so that was pretty much all, except that I'll have some notes for inductive invariants or invariant inferencing in the end, and I'll tell you how these guys try to construct the invariants. Anyway, yeah. So getting back to recurrent neural networks, so we know that these are kind of DNNs, and of course they have the ability to store information because you want to reuse information from the previous context or from the previous run. So, of course, they're suited, therefore, for tasks that involve context like machine translation and speech recognition and so on. But like any other DNN, they are vulnerable to adversarial inputs, and therefore there is a need to formally verify. And the formal verification, of course, can be done when you unroll them into what are called feed-forward neural networks, whatever we had been seeing so far. But this is not very good for verification because the verification exercise is exponential in the size of the network, and therefore this is discouraged. Okay, so we had looked at this simple example where you had this input neuron 1, 1, from where you were going to 2, 1. This is the hidden neuron. There's only one hidden layer which has only one hidden neuron. It has a memory unit which is 2, 1 tilde, shown as the square box on top. And of course, the first time that this is executing, there's nothing in the memory. So that does not contribute anything to the value of 2, 1, v2, 1. But later, from the next time step onward, starts contributing. So in this one, how it contributes is as follows. So you get some input in the beginning. So this is half is what you get at 1, 1 at time step 1. And this half is propagated to 2, 1 because there is an edge of weight 1. Okay. And nothing comes from the memory because this is just the first time step. So it is half that gets to the output as well. So which is 3, 1 here. Okay. So then what happens? You move to the next time step. So you get 1.5 as input this time. You get half from the memory. So together you get 2 at 2, 1. And this 2 is what gets propagated to 3, 1. Once again, you get -1 as the input. and then you get 2 from the memory. So together you get 1 at 2 comma 1, and 1 is what gets propagated at 3 comma 1. Okay. And then in the fourth step, you get -3 as the input. You get 1 from the memory. Sorry, you get 1 from the memory. No, 2 from the memory, is it? Yeah, 2 from the memory. And together, the whole thing is negative, which is why it is reduced to 0 by the activation function, which is relu. And 0 is what gets propagated to the output. Okay. So this is all very simple stuff. Okay, and then of course, since we are talking about verification here, so how does a verification query look like? It has 4 parts. So it has a precondition. So in this case, for this example, we were looking at a property which had the precondition that all inputs lie between -3 and 3. Of course, you have the network, which is the network that you had seen earlier. And you have a post condition which says that the output is greater than or equal to 16 at least once. And the fourth component is time. And in fact, so that's why in the precondition and the post condition, you have phrases like all inputs and at least once. So there is this notion of time, and it says that time. So so the property has to be understood in the way that that it will hold for this time duration, which was 5 in this particular case that we were looking at the last time. Of course, as I had remarked earlier, you can transform this RNN verification problem into a feed-forward neural network verification problem by unrolling. Okay, so you can unroll for 5 time steps, which is your Tmax. So you can unroll this for 5 time steps, and this red edges that move rightward in the center. So these red edges fill the role of memory units, and you can verify your output, all 5 outputs. So you can actually verify this property, this post condition. Except that the network size is increased 5-fold, and that is not quite desirable. Okay, yeah. So this is some text that I've copied from the paper. I'm sorry about it, but I just wanted to recap what we had seen that day. So this is, yeah. So of course, one way is to transform this RNN verification problem into feed-forward neural network verification problem by unrolling. Okay, but that's certainly not very desirable. So this one we talk about how to circumvent unrolling. So for that, they propose certain transformations. Okay, so you had this precondition, you had the network, you had the post condition, and there was this Tmax. So they say that, look, you can get rid of Tmax, and then you can modify your preconditions, post conditions, and the network in such a way that you can transform this to a feed-forward verification problem, which we know how to do because we have seen things like reluplex. Even Z3 to some extent can be used, of course, depending on how far it scales to. Okay. Yeah. So what does the transformation look like? So the transformation is very simple. So for the network, what do? You add 1 neuron to represent the time, which is the T neuron that we had seen the last time. You have 1 more neuron for every memory unit, which is brought to the input layer. So for every neuron that has a memory unit, you add 1 neuron to the input layer, and then from that neuron you add an edge connecting it to its corresponding neuron in whichever layer it is. Okay. So in fact, this is an exception here. Normally transitions are not allowed to jump layers, but this one is allowed to jump. Okay, so these are the only 2 changes to the network. The post condition does not change at all. The property changes in this particular way. So the property, so earlier you had this post condition. Earlier you had this precondition P. So now your precondition has three distinct parts. One is P itself. One is a constraint on the time neuron that you have added. And the third one is a constraint on all the other memory neurons that you have added. Okay. And we'll see what these constraints look like. Okay. So this is once again transforming the problem of RNN verification into feed-forward neural network verification, but this is without unrolling. Okay. So as you can see, yeah, as you can see, so we have added this this neuron, this T neuron here, and there's a 21 memory neuron which has been added to the input layer. The transition, of course, looks normal here, but even if the neuron was in a deeper layer, there would have been a transition from the input to the deeper layer. Okay, so this is what the network looks like, and then what does your verification query look like? Your verification query looks like what it has been shown below. So remember that it had three components, which is what we spoke about. So the first component, I'm looking at P. So the first component of P is this conjunct where we say that the input has to lie between -3 and 3, which is what the original precondition was. The second conjunct says that the T must belong to something between 1 and 5, which is true because we want to check whether this property holds for 5 time steps, starting from 1, of course. Okay, so this is the constraint on T, and then you want to put certain constraints on the memory neurons, and so this is one constraint that they have put on memory neurons, that 21M is less than equal to 3 times T minus 1. Now it's not clear how do you get such constraints. It's not even clear that what kind of constraints are useful. For instance, I could have a very relaxed constraint saying that V21M lies between -infinity to +infinity. Okay, which is as good as not putting any constraint at all. Okay, but the downside is that it's not even useful. How do you use this constraint, or this how do you use this precondition that 21M lies between -infinity and infinity? Okay, so the point is that you need some such constraints on, or some such property about these memory neurons, but this property has to be nice. What do you mean by nice? By nice, I mean that it has to be useful for the verification that you're doing. Okay, and therefore it becomes important to get nice properties here. Okay, so what we'll get as properties here are invariants, and by nice we mean that we will get invariants that can prove the property. So we'll get invariants that are sufficiently strong to prove the property. They are not needlessly strong, and they're certainly not weak that they cannot even prove the property. Okay, so whenever you're trying to get such properties like the third conjunct shown here, it becomes important to get what is just right, because of course getting them right is a difficult problem in itself, and therefore so the point that I'm trying to make here is that getting the third conjunct is a difficult problem. It's not solved, and it has to be done such that your post condition can be discharged, whatever your post condition might be. So it's not independent of the post condition. You want a property which is strong enough, which can discharge your post condition. Okay, so let's just keep these things in mind, and then we'll see more when we go to inductive invariance. Okay, which is right now. Yeah. Okay. Yeah. So this was about so this is what we had looked at the last time, except that for the third conjunct we had decided that there are two things that are important. First of all, we need to know that whatever has been written here is correct. So we need to know that the V21M is less than equal to 3 times T minus 1 is indeed a correct thing. Okay. And the second problem, of course, is to obtain such a thing. How do we get such a thing is not very clear. Okay. So we had seen the last time that checking the correctness of this can be done by induction. So you can check whether this is correct in the beginning, and then starting from a place where this is correct. If you somehow take one more iteration, it continues to be correct. So this induction thing actually very closely relates to what are called inductive invariants. So therefore, let's take a look at what are inductive invariants, and then we'll come back to this. Yeah, but at this point, if you have any questions about whatever we have seen so far, then it would be good to address them right now. Okay, so assuming that there are none, so let's look at inductive invariance. Okay, so let's consider this program that you see on the left. Okay, it's a very simple program. What it does is it starts with x and y both set to 0 in the beginning, and then in a loop which runs an unknown number of times, you increment x by 1 and then you increment y by x. So this is what you do every time. Okay, and then you need to argue that when you exit out of this loop, y will always be greater than or equal to 0. Okay, so if we try to see why this is correct, why should this assertion really hold, then we can convince ourselves in some way, right? What is the way in which we can convince ourselves? We can see that x and y are both 0 in the beginning, and then we don't know how many times the loop executes, but we know that only positive things are being added to y, and assuming that these are mathematical integers which do not overflow, it is true that if y was 0 in the beginning and if only positive things are being added, then there is no reason for it to become less than 0. So it will continue to be greater than or equal to 0. Okay. Now this is what we want to derive, but we want to make an argument which can follow some logical steps. Okay. And therefore, what we try to derive for a loop, for any loop, when we are doing program verification, or when we are trying to prove such properties for programs like this, since we cannot argue about this loop at once, we try to derive loop invariants for this loop, so that then we can argue about the loop at once. So that's the general idea. Okay. Okay. So what we do is we try to derive what are called inductive invariants. Okay, so of course I'll get to the formal definition in the next slide, but before I get to that, what are inductive invariants? So inductive invariants are things that are true when you are entering the loop for the first time. Okay, this definition is very close to that of induction, but we'll see that later. Okay, so inductive invariants they have to be true. If you have an inductive invariant, it has to hold good when you are entering the loop. Okay, so that's one thing. Okay, and the second property is actually the induction property, which says that if it holds true at any point in time, then one more iteration of the loop will continue to preserve it. Okay, so now let's try to see some candidates here. Okay, so first of all, the claim is that x is greater than equal to 0 is an inductive invariant. Okay, why is it an inductive invariant? So there are two things that we have to check. Okay, so we have to check that x is greater than equal to 0 holds in the beginning when you are entering the loop for the first time, which is true. Since x is equal to 0, x is also greater than or equal to 0. Okay, so this holds. Okay, but then you need to check the inductive step. The inductive step tells you that if x is greater than or equal to 0, then one more iteration of the loop will preserve it. Okay, so what happens in a loop iteration? The x changes because x is increased by 1, and y changes, but we don't care about y because we are worried about x right now. Okay, so we knew that x was greater than or equal to 0, and now the loop iteration increments x by 1. So then from these two, we can derive that x will continue to be greater than or equal to 0. Right? So therefore, it is inductive. Okay, just to put this in contrast with y greater than 0, which is not inductive. Let's try to understand why it is not so. Okay, so y greater than 0 of course holds in the beginning because y is also 0. So therefore, it is greater than or equal to 0. Okay, but why is it not inductive? Because if you know y is greater than or equal to 0, then if you take an iteration of the loop, then y is incremented by x. Okay, and now you cannot say anything about the final value of y. You cannot say that it will be greater than or equal to 0 in absence of any other knowledge, is what we are saying here. Okay, so if all you knew is that y was So if all you knew is that y was greater than equal to 0, then you cannot conclude that y will continue to be greater than or equal to 0. Okay. So therefore it is not inductive. Okay.
Yeah, I think I just want to add that I think that's because you can't assume anything about x. Okay, so when you prove inductiveness of y greater than or equal to 0, you starting from an arbitrary state in which y is greater than or equal to 0, which means x can be anything. Okay, so x can be anything. So that's why, so there is no guarantee that when you add y, change y by adding x, y doesn't have to be greater than or equal to 0. Because, yeah.
Correct. Yeah. So without any other information that you have, you cannot say that y greater than 0 is inductive. Of course, if you add the information that x is greater than equal to 0, so for instance, if you take this conjunction that x is greater than equal to 0 and y is greater than equal to 0, you can see that it is inductive. Okay. So knowing that both of them are positive, you can conclude that both of them will continue to remain positive. Okay. So this is so therefore this is an inductive invariant. Okay, and x is greater than equal to 0 is also an inductive invariant. Okay, so now there's also this question about safety. Okay, so you also want your inductive invariants to be strong enough to tell you that the property holds. I mean, of course, for correct programs only. But assuming that the program is correct, then you want your invariants to be strong enough to give you the property x greater than equal to 0. While it is inductive, it is not strong enough to prove the property, which is why we say that it is not safe. Basically, it means that it does not imply that that the property holds. Okay, but this conjunction, which is certainly inductive, is also safe. It tells you that if you know that x and y are both greater than equal to 0, then you know that from this you can derive that y is greater than equal to 0. Okay, it's just one of the conjuncts. Okay, of course, this is not just the only example. This is not the only example. There are other examples of invariants which are inductive as well as safe. For example, x greater than equal to 0 and y minus x greater than equal to 0 is another example of an invariant which is inductive and as well as safe. Okay, so in some sense, so this is what I was referring to at this point, that at this expression that you have in 21M, you want this to be, in some sense, this has to be correct. So this has to be inductive, and this also has to give you the safety property. So this also has to be strong enough that along with other preconditions and the network, it can discharge the safety property. It can discharge the post condition. Okay, so you need this to be good in all these senses. Okay, and there's no one thing which is good, as you can see here. There's no one thing which is good. There can be multiple things which are good and useful for you. So you just need to find out which one. And inferring inductive invariants is a difficult exercise, but we'll get to that. But let's get to the formal definition first. So here, of course, init implies the initial condition. The TR is the transition relation of the loop. Bad is the negation of the property. The property is that y is greater than equal to 0. So bad is negation of y is greater than equal to 0, which is y less than 0. Okay, and v and v prime are just the set of variables which are primed for the next step. So basically, whatever when an assignment happens, you basically the next state variables are the primed variables. Okay, so this is what this thing is, and for an inductive invariant, it should satisfy. So whatever we have said is belongs to these three things. So we want our invariant, we want our candidate to whatever candidate we may have for inductive invariants. So if the candidate satisfies these conditions, it is called an inductive invariant. So these are two conditions that the candidate is expected to satisfy. One is called initiation, which says that the init implies the invariant. So whatever holds in the initial state should imply the invariant. And there's this thing called consecution, which says that if you know the invariant, then if you take the transition relation, you will know the invariant in the next state also. Okay, and let's look at this in some detail. So you have these these primed and unprimed variables, which is x and y, and then since they are both written to in the loop, then you have x prime and y prime as well. What is the init condition? Init is what you see in blue here. So init is x is equal to 0 and y equal to 0, which was your initial state. Okay. So this is the init. What is the transition? The transition says that x prime is x plus 1, which is x is incremented by 1, and y prime is y plus x, as it is here in the loop. Okay. And what is bad? Bad is the negation of the assert, which is negated y greater than equal to 0. Okay. Okay. So we want to. So what are we trying to do here? We are checking that this thing that we said, that x is greater than equal to 0 and y is greater than 0 is an inductive invariant. We are checking that it is actually so. Okay. So to check that it is so, you need to do two checks. Initiation check, where you check that x is equal to 0 and y equal to 0 implies x is greater than equal to 0 and y is greater than equal to 0. Now this is a valid check. Okay, so this is a valid implication. Okay, and you can use an SMT solver to check whether your implication is valid or not. Okay, so first of all, this is a valid implication, so therefore your candidate passes the initiation check. Now we'll check for consecution. So how do we check for consecution? We say that x is greater than equal to 0 and y is greater than equal to 0. So you take the invariant, then you take the transition relation. And if this implies the invariant for the next state, if this holds, once again, if this implication is valid, then you know that the consecution property holds. And for a candidate, if you know that the initiation holds and the consecution holds, you know that it is an inductive invariant. Of course, it may not be safe, but that's not, it's not important for an inductive invariant to be safe. Safe inductive invariants are desirable, but you can get a number of inductive invariants together, they can be safe. So safety is another quality. This is not about inductive invariants. Okay. So an invariant is inductive, or a candidate is an inductive invariant if it satisfies these two tests: initiation and consecution. Okay. Now, of course, this one turns out to be safe as well, and the way to check it is that you conjunct it with bad, and you should not. This should not be satisfiable. The conjunction of the invariant with bad should not be satisfiable at all. Okay, so this one should be false. Okay, so any questions at this point? Because this was not a program verification course, so therefore, I mean, of course, this was still, we were trying to do verification here, but this might be new to some of you. So do you have any questions?
Yeah, I just want to add one point, Madhukar. So I think here the safety will have the bad part, and in this case, and also the loop, the negation of the loop condition. In this case, the negation loop condition was true. Okay, so in general, if it was a terminate, so because it was true, correct. So if you had some loop entry condition, then you will also have to include the negation of that, because
correct. Yeah. So what sir is saying, that if you had a different condition here than star, so if you let's say if you had a condition C here, then when you are outside the loop, when you're just outside the loop, you can assume not of C, and this assumption of not of C can help you at times. In this case, of course, it was not needed, but you can assume not of C when you are outside the loop. And this extra knowledge that you have about C not holding outside the loop can help you discharge the property in some cases. Is this what
correct.
You're saying?
Exactly correct. Yeah. And also because you will reach that exit only if that negation is anyway. Yeah. Only if not of C holds good. Good point.
Correct.
Yeah, but what you said was correct too. Sometimes just the invariant itself might get you there, but in most cases for program verification, you need the not of C.
Correct. you need the not of C, and yeah. In fact, sometimes it can also tell you whether the assertion is reachable or not. For instance, if you have a while one loop or while true loop, and then there's an assertion outside the loop, it does not matter what the assertion is. This program is, I mean, of course, this program can still be considered safe because you will never exit out of the loop. So not of true will never hold. Okay, because if you exit out of the loop, you must assume that not of the loop condition holds. Okay, so if you have a while true loop, then you cannot logically, you cannot come to the exit of the loop because not of true will not hold. Anyway, yeah. Okay, so this is what we had to say about inductive invariance. Okay, and then coming back to this thing, because what we are primarily addressing is this problem of RNN verification. So what we need here is inductive invariance. Okay, and of course getting inductive invariance is a difficult exercise in itself. Okay, but once again we'll hold this discussion for some more time, and let's see why. Okay, why this 3 times t minus 1 is an inductive invariant here. Okay, so what I've done is I've written this toy RNN that we had as a program. Okay, so this is a very simple program. We have written neural networks as programs earlier also, and there's nothing very fancy about them. Okay, so it's nothing. It's a bunch of computations that are happening in some sequence, and then you try to write that same thing in a sequence. Except in here, since it's an RNN, there is also a loop, so we have tried to write down that loop. Okay, so you have this t, which denotes the time, which is 1 in the beginning. There are also these other real variables. The memory variable is certainly 0. Okay, and then while t is less than equal to 5, you get an input, you assume that it belongs to -3 and 3 because that's your precondition, and then the standard set of computations. So what is it that you're doing when you're computing it? So you set 21 to be the sum of 11 and 21 memory. 21 memory, of course, has 0 in the beginning. And this is just one part of the computation. Remember that 21 is a ReLU node. So if 21 is less than 0, if the value is less than 0, then you set the value to 0. Okay. Then you store whatever value you have into the memory, and the output, of course, there is an edge of weight 1, if you remember, from 21 to output. So output gets the same value as 21. Okay. And then every time you get the output, you assert that it is less than equal to 15, because if this is violated, then you know that one of the time the output was bigger than 15, which was the verification query, that it is greater than equal to 16. Okay, so you assert in the loop that output is less than equal to 15, and of course you increment time by 1. Okay. So now for this one, if we want to prove that V21M is less than equal to 3 times t minus 1, can you prove that this is an inductive invariant? This is I'm saying this as an exercise here right now. Can you argue that this is an inductive invariant? Remember that there are two things that you need to check when you're checking whether something is an inductive invariant. So you need to check that it holds when you are entering the loop for the first time.
Yeah, but yeah, one thing, I guess. Okay, one point that before you address that's correct. So the that condition that you had is actually required. Okay, so because V31 being less than or equal to 15 is what you want to prove, is what we want to prove. And that in itself is not an inductive invariant. Therefore, you need something like what you just now said, which is some constraint on V21M. Correct? So that is
correct.
yeah. So that is this. Since this is not, if V31 less than or equal to 15 itself was inductive, then you don't need anything. So here, because V31 less than or equal to 15 is not inductive,
correct.
And therefore you need a suitable inductive invariant. And now you're proposing that what you had earlier seen is an inductive.
Correct. Yeah. Okay. So just to put this remark in perspective with the earlier example, so here also remember that you wanted to prove that y is greater than or equal to 0 holds when you exit the loop. And it would have been convenient if this itself was an inductive invariant, but we found out that it is not. It was not an inductive invariant, because if you knew that it holds, and if you try to take an iteration from there, then you could not guarantee that it will continue to hold. Okay. So in general, when you're doing such verification exercises, it becomes very natural to check whether the property itself is an inductive invariant. Okay. And therefore, even for this exercise, we could check whether 31 less than 15 itself is an inductive invariant. Okay. And it is, yeah, it's not, you can argue that this is not an inductive invariant.
Because if you don't know anything about V21M, since V21M can be anything, and that's what is being added to V31, so you can't say anything about V31. That's why you need some constraint on VT1M that is inductive and invariant.
Correct. Okay. Yeah. So just to repeat, So how is V31 constructed? It's constructed from, so V31 gets the same thing as V21, which gets the same thing as V11 plus 21M. Now 11 is something which changes in every loop iteration, and you know what it can be. It can only be between -3 and 3. But 21M you don't know anything about, right? And that's why sir was saying that it's important to derive some constraint on 21M. Because on 11 you have some constraint. 11 you have the constraint that it's always between -3 and 3. So 21M is the only additional thing that V31 is affected by. So therefore you need, without any constraint on V21M, you cannot say anything. But so therefore there's a need to constrain this in some way. Yeah. Okay. Yeah. So can you argue that 3 times T minus V21M is less than or equal to 3 times T minus 1 is an inductive invariant? This is the exercise that we are trying to do. Yeah, anyone?
Yeah, because I mean V21M is initially 0. So since T is initially 1, it holds initially.
Correct.
And at each point we are adding like something that is less than or equal to 3 to V21M. So we can use that fact to say that when T goes to T plus 1, V21M will at most go to V21M plus 3. And that will give us the inductive condition.
Correct. Yeah. So once again, very simple. So you prove the initiation, which is very simple because T is 1 in the beginning. So T minus 1 is 0. So V21M is less than or equal to 3 times 0, which is 0. And since it is 0 anyway, so 0 is less than or equal to 0. So you are good. Okay. So then you need to argue about consecution. So in consecution, so you can assume that it holds. So you assume that V21M is less than or equal to 3 times T minus 1. And then you take one more iteration. Of course, your T increases by 1. Okay, but what you add is certainly bounded by 3. Okay, so therefore, from these two facts, you can derive that V21M will continue to be less than or equal to 3T minus 1. In fact, so now I'll get back to the paper. Just one second.
Yeah, but of course you will need that T is less than or equal to 5, which is true inside the loop. all the time. So you need t less than or equal to 5 also as a condition.
Which one?
No. Just that alone is not enough.
Correct.
You need t less than or equal to 5 also,
Correct.
which is also an inductive.
Correct. Yeah. So we'll come back to that. Yeah. Okay. So this is about checking whether this is an inductive invariant or not. And yeah, so remember last time we were seeing this, and we saw that there are two checks that has to be done. So one of the checks was something very simple. You had to check that 0 is less than or equal to 3 times 0, because this is fine. So initiation check was fine. The other check was constructed as a feed forward neural network verification query, and you can make that query, but essentially what you're checking is just the consecution property. Okay, so which is what this covers, this section covers.
Yeah. So it may be instructive to add that what the feed forward neural network is exactly the body of the program that
correct
that you saw. So that's why you could use the feed forward network with whatever the modification that he has to that was made to check. Okay, so you assume that it is so that.
So what sir is saying is that, look, while the consecution check does not worry about the loop, it only worries about the body of the loop. Now the body of the loop can be thought of as a feed forward neural network, and therefore the consecution check can be encoded as a feed forward neural network verification query. Okay, which is
exactly what the paper does. Yeah.
Which is exactly what the paper does. Yes. So yeah, of course, the other point which the other thing that sir made a remark about was that, look, you know that V21 memory is less than or equal to 3 times t minus 1, but that alone does not tell you that the value at the output will be less than or equal to 15, because if t is not bounded, how can 3 times t minus 1 be bounded? Okay, so therefore you need a bound on t, which is, and of course, t lies between 1 to 5 is another inductive invariant of this thing. So just 1 second. Sorry. Yeah, sorry. So this yeah, so you need something more. Just 3 times t minus 1 is not going to suffice. So you need this bound for t, which says that t will lie between 1 and 5, and together with the original precondition, your property can be discharged, and that's the whole idea. Okay, yeah. So this is so far about sorry. Yeah. So this is what we have seen so far about this RNN verification query, that it relies on finding what are inductive invariants, and then with a suitable, if you have managed to find a suitable invariant, then you can discharge your property. Okay, you can transform the whole problem as a feed-forward neural network verification problem, and then you can discharge your thing. So there are two things which are important to understand here. Okay, so first of all, this transformation is an over approximation. Okay. So this transformation is an over approximation, and therefore, so if your invariants, if your invariants are very big or very broad, then you may not, your feed forward verification query will fail, but you will not be able to remark anything about the RNN verification query. Okay, so it's an over approximation. So it gives you answer only if it is successful. If that verification query fails, if you get a counterexample, it does not necessarily translate to a RNN counterexample. Okay, if you get the property as safe, then your RNN was certainly safe with respect to that property. Okay, but if this one fails, then you cannot say anything about it. Okay, and why will this one fail? If you have a very broad invariant, if your invariant includes too many states, okay, so then this is likely to fail. Okay, so that's one thing that we have to understand here before we move to invariant inference. Okay. Yeah. So in invariant inference, see, of course, so I mean, just a little bit of background on invariant inference. See, invariant inference is a difficult exercise. I mean, of course, the problem in general is undecidable, and therefore people have done so many things. So there's an enormous amount of literature on this. Okay, but we don't have to worry about that. This paper suggests something very simple. So they say that our invariants are going to be of this form. So they'll be some lower bound times t minus 1. So any memory node will lie between some lower bound times t minus 1 to some upper bound times t minus 1. Okay, so they have simplified the entire exercise as this. Okay, so they take a memory node and they say that, you know, this memory node will be some, so they try to find this lower bound and upper bound such that this memory node's value is contained in this range. Okay, so this is fixing such a template and then trying to find these values. Okay, this is all that they are trying to do. Okay, which is not very, you know, if you have been doing program verification, or if you have been trying to find invariants for programs, this is not very interesting. But of course, you know,
that is, I wouldn't say, I mean, I don't know. See, because abstract interpretation exactly does find these kinds of invariants, no? So they are, you know, the abstract, for example, what they're doing is trying to find an interval in which that bounds the value of the memory thing. Okay, the memory.
Correct, but here, yeah. correct. Here, but here they believe that it's only related to this only other variable called t, is what I was pointing to. In general, you cannot.
No. This is, I know this may not, just deriving these kinds of invariants may not be sufficient in all cases, but it can get you, you know. So this is interval invariance. Okay, so they're restricting themselves for interval invariance is the way that I would consider. So they have to find alpha L and alpha U, correct? So,
correct. So they have to find.
So abstract interpretation does exactly that. Yeah. I mean, abstract interpretation is one method of doing it, but you know, so maybe they're suggesting something else. Yeah. But what I'm saying is, and the only point I'm making, the limited point I'm making, is that while these may be restrictive in the form of invariance, but they still get you a lot of you know, a lot of mileage in some cases is all I'm saying. So,
correct. Yeah, agreed. Yeah.
I mean, especially here, if they are only interested in the kinds of properties which are also interval bounded, okay, lower bound and upper bound, which is what they had, correct? So then, even then, you know, maybe you need more stronger invariants, but this is a place to start. Okay, that's the only limited point I'm making. I'm not, I mean, I agree with you that this may not work in all cases. Okay, so that.
Correct. Yeah. That's what I meant. Except that, yeah. So I was referring to the fact that so they are referring to. I mean, this T is the loop counter in some sense.
Oh, okay. Mm.
So it's yeah. So the invariant that they are looking for is that at any point of time you are from some multiple of loop counter to some other multiple of loop counter.
Mm.
Which looked a little restrictive to me, but yeah, I agree to your point that this itself can give you the desired property in many cases. Yeah,
especially if the property that you want, of course, it depends on the property. You're correct. Okay, so
Correct. Yeah. Anyway.
Hmm.
So yeah. So this is the idea. So the idea is that so they say that look, we are going to look at this template, which is nothing but it is always going to be some multiple of t minus 1. So you're always going to lie between some multiple of t minus 1 to some other multiple of t minus 1. And these lower, these alpha L and alpha U, which are the multiples of which are the coefficients that you use to multiply. So this is what has to be found. Okay. And that's the idea. So the idea is that this is how they do it. Okay. So first of all,
do they restrict themselves to these kind of expressions? That is 3 times the time. I mean, some linear expression involving the time parameter. Is that the restriction that they impose?
no, they always use t minus 1.
No. But here, the expression was 3 times t minus 1. So some linear expression. Some linear expression involving t or t minus 1 or whatever. Yeah.
Correct. It's always some constant into t minus 1. And this constant is what you're trying to derive. So basically some multiple of t minus 1, and what is that multiplying factor is what they're deriving. So of course, I mean, there's nothing involved in that whole process. See, the deriving that thing is not, so there is no derivation here. So what you do is you know that it is going to be some constant multiplied by t minus 1. So you try for some constant multiplied by t minus 1. If that is good, if the proposed invariant, remember that from the earlier section, remember that you could transform this into a feed-forward neural network verification exercise, whether a given invariant holds or not. So you try for some constant. If it is good, then you are good. Otherwise, you tighten the invariants. So that's the entire exercise. Okay. So you assume that your things are going to be linear templates. Okay. And then in these linear templates, you have to find out the lower and the upper bounds. So you try for some lower and upper bound. If that happens to be an invariant, then you are good. If it is not an invariant, then you will get a counterexample to the property. And then using that counterexample, you can tighten your invariant. You can make it too strong. I mean, if you can realize that it is too strong or too weak, so then you can try and strengthen or weaken it. Okay. So I'll quickly go through this part, which tells exactly what they're doing. Okay. So of course, the template. So now you just need to find out the right alphas. Okay. So the idea is that you propose an alpha and then you check whether it is an invariant or not. Of course, checking whether it is an invariant or not is something that we have seen already. Okay. So they say that there are 2 places where this process might fail. Okay. The first thing is that the proposed invariant cannot be proved because you have a counterexample to the safety or to the inductiveness. Okay. So the proposed invariant is not inductive. It's unlikely that it will fail even for the initial case. If it fails for the initial case, you need to modify it. But suppose it fails for it succeeds the initial case and it fails only in the verification query, the feed forward verification query that you constructed from your consecution check. So if it fails the inductiveness thing, then there is a counterexample, which means that the invariant is very strong. So which means that the bound is very tight, and therefore you need to relax the bound. Okay. The other thing is that the invariant will hold, but this is not useful, in which case the invariant is very weak, and therefore you need to tighten the range. Okay. And this is done by decreasing the upper bound. Okay. So in one case you are increasing the upper bound, in one case you are decreasing the upper bound, and symmetrically for the lower bounds. Okay. This is all that they do. Okay. The point is that this itself is good enough for a class of RNNs. Okay. So what does so this is the algo that they are proposing. Okay. So they start with some large upper and lower bound. Okay. And then while these upper and lower bounds do not converge to something small enough, they keep doing this check. So they pick an upper bound and pick a lower bound, and then they fix their invariant. See in line number 3, the invariant is always fixed to be alpha u times. I mean, this, of course, this is only for alpha u. There's a similar thing for alpha L. I mean, it's just symmetric. Okay. So the invariant is always fixed to be of this form, that V21M is less than equal to u times t minus 1. Okay. And then depending on what you get as a result of your verification query, you either increase the alpha u or you either decrease the alpha u. Okay. So this is what your verification, so this is what your verification algorithm looks like. Yeah, is this clear? Am I making sense? Or
Yeah, any questions? Yeah, yeah, any basic questions about inductive invariance and so on. So after that, I have a few comments to make about by comparing this inductive invariance. So first, let's take their questions. Any questions on the basic concepts of inductive invariance, you know, those 3 conditions that Madhukar laid out, you know, that define what an inductive invariant is, and how that is, you know, how the paper reduces, I mean, applies this to the RNN in particular. Okay, so that's why, you know, Madhukar used this contrast of, you know, an RNN basically is like a loop program, the body is the actual feed-forward network. Yeah, any questions there on the basic part? Because that's some of the key takeaways from this lecture that we wanted you to take home. Okay, and that is important for you to know. Okay. Yeah. So the general, I mean, yeah, if you, yeah, you can ask questions later as well. So the one comment I wanted to make, one was general. See, this area of generating inductive invariants that fit various shape is a very active research area. So there are lots of techniques, you know, for synthesizing these invariants, some of which also, some of them are purely logically based, some of them, you know, do some syntax guided thing. There are a whole range of things. Okay? Lots of things, and some of those some people have also looked at using machine learning to generate these things, but that's so it's a very broad thing. So the only thing I think we could say is that you know, there's a lot of active research in that area. But one specific comment, there's one particular tool. This is where Madhukar, that I was surprised, because 2LS, there is a particular tool called 2LS. Okay, it exactly does this. Okay, so it derives even more sophisticated invariants. It can, here they're restricting themselves to, I mean, they're just template shaped, but there are, what I'm pointing out is there are, you know, tool. One of the ones that I mentioned was 2LS, where if you restrict yourself to the invariants to be of this kind of template. Here, the template is very much like a particular variable has to be between, you know, this is basically a linear constraint, okay, on the variables involved, okay. So that is usually called a polyhedral template-based invariance. And this tool called 2LS, the abstract interpretation that I talked about, is one method. Okay, but here the unique aspect is that the search is done using this while loop, but inside that you see that he is using SAT solver, okay, an SMT solver, to check whether these things are inductive or not. If not, he has to learn from the counter example and do that search in a reasonably efficient way. There are actually, you can do what are called binary search and so on, so that you don't, you get to converge. So there are tools. One such tool is 2LS, okay, is from Oxford, where they restrict themselves to these kinds of template-shaped invariance for, it's targeted towards programs, okay, C programs. So it's not, pie in the sky. So there are actual real systems for which it sometimes works, and sometimes it can run out of steam. Okay, so in that sense, the inductive invariant inference part, at least doing linear invariant, is a well-studied thing. So there are several different approaches. But the curious thing is that the important thing to notice is that in these kinds of things, SAT SMT solver is at the back end, trying to check for inductiveness, and then there's a layer which does the search for the appropriate bounds. Okay, so that's the.
Yeah.
Yeah, the point, I mean, Madhukar, that I wanted to make, thing is that this in itself is, 2LS does this, okay?
Correct. 2LS, of course, has support for more templates, in the sense that this is...
Yeah, it's even more sophisticated template. So this aspect of it is not the novel part of this.
Correct, yeah. Searching for a linear, searching for an invariant in a linear template is not, certainly not novel. It is using an existing technology. So in fact, this idea of picking a template and then the parts of the template which are not fixed, for instance, these constants and coefficients.
Mm-hmm.
So you can pick a template, and then you can assign your own constants and coefficients, and you can check. So this kind of a guess and check framework exists for finding invariants. So people have worked on templates in which some of these coefficients, or sometimes even these operators, you can leave the place for the operator. So you know that X and Y have to be related, but you don't know which operator. So you can fix your template at any level. You can even leave placeholders for operator or variables or whatever. So you can fix a template in however many details you want, and then the remaining parts in the template you can fill. So you can either fill by knowing something, or you can simply guess some way to complete this template, and you can check whether it is an inductive invariant or not. So this kind of a guess and check framework is also common for finding inductive invariants.
And they actually extend to much more than linear templates, don't they?
Correct. Yeah, it could be anything. Of course, once you get to non-linear, even checking that it is inductive is more expensive for the solver. But at least there is a way to guess and check, and this is what these guys are doing. So they're guessing a value for the upper bound and the lower bound, and they're checking whether this is correct or not. So this 3 is obtained by actually guessing. Okay, and then of course you can start with a big enough bound. So this 3 is actually obtained by starting from this minus m to m. So you don't know what this upper bound should be. So you say that, okay, it could be anything between, let's say, minus 100 to 100. And then you try and make this thing better and better and better in every iteration, and somehow arrive at some number 3, which happens to work. Okay. So every time you try to restrict the bound, you either try to pull the lower bound, or you pull the upper bound or push the lower bound. And then you try and guess better and better. So what is really happening in every iteration is that your guesses are becoming better and better till you hit a guess which happens to work for your case. Okay, so this is also an instance of once you fix a template, you guess certain values and you check whether the invariant is sufficient or not. And this guess and check kind of thing is common for finding inductive invariants for program verification as well. Okay, so there are some last bits which are remaining. Okay, so of course this is, yeah, so this, remember that what did we try to do?
Full screen?
Yes, sorry.
Is it full screen? Maybe
this is full screen. I can make it.
Okay. Oh, no. Okay. So, but you were.
Yeah.
Yeah. Okay.
Yeah. Sorry. So just a couple of more remarks. Nothing. So this paper does not. This paper, roughly, this is what this paper has. So just a few remarks. So first of all, this is only about a single memory unit. So right. So you took this one memory unit and then you try to put lower bound and upper bound. And in that also you said that, look, the lower bound is symmetrical to the upper bound. So let me just focus on the upper bound. And thereby you got this algorithm to fix your upper bound. Now a similar thing for lower bound whenever it is needed. But this is only about one memory unit. Okay. Now, of course, it has to be extended. So the way they extend it is as follows. So what if you have multiple memory units in separate layers? So in each layer, you still have one memory unit, but in a different layer, you can have one more memory unit, and a different layer, one more memory unit. So then how this is done is that, this is done in an iterative fashion. So you find an invariant for the first unit in the first layer, and then you move to the next layer and then try to find an invariant for these two, and then so on and so forth. So you go layer by layer trying to find an invariant for everything. Whenever you are checking for the next layer, you assume the invariant in the previous layer to hold. Okay, so this is an iterative algorithm to check multiple memory units in separate layers. Okay, now of course this becomes more problematic when you have. Okay, so if you want to understand this in terms of loops, this says that, what are multiple memory units in separate layers? These are like multiple loops, one after another. Okay, so you have one loop, then after that you have one more loop, and then after that you have one more loop. And how you can solve this is by finding an invariant for the first loop, and then going ahead finding an invariant for the second loop, then going further ahead finding an invariant for the third loop, and so on. Okay, so this is in terms of, if you want to think in terms of loops, this is what it is. Okay, the problem comes when you have nested loops. Okay, and this nested loop is nothing but layers with multiple memory units. So now if you have two memory units or more than two memory units in the same layer, this becomes a problem. Like how it becomes a problem when you have to find invariants for the nested loop. Okay, so in nested loop, it's not clear how you find an invariant, right? Because nested loops are a problem. I mean, just to give you an idea, see, what is it that you were doing earlier? You were checking whether, something is holds true initially, whether something satisfies initiation, and then it satisfies consecution also. So for consecution, you assume that the body of the loop. Now, the body of the loop itself has a loop. In nested loop, the body of the outer loop has a loop has a loop inside. Okay. So therefore, it becomes a problem. Similarly, here, layers with multiple memory units become a problem. Okay. So therefore, they have sketched a solution. I tried to read through it. It's not very intuitive, and there are too many ifs and buts. So I don't have a presentation ready for this. In fact, I don't even understand this very well. But this is when it starts getting a little complex.
But have they solved the problem for nested loops?
No, they have not solved. So what they say is that this is yeah. So what they say,
simple. I mean, I'm not asking for your explanation on just a simple answer whether they have a method, or I mean, it is known that for nested loops, it is a hard problem. Okay, and there are some methods, but I mean, I'm wondering if they have also proposed some new methods. That's all. That's all I'm asking.
Correct. No. So since it is all guess and check, so their idea is that, look, you try and find something for the first one, and then for the second one, and somehow it happens to be an invariant together.
Okay.
But there's no method developed for, because they say this entire exercise is a guess and check thing.
Yeah.
So therefore, what they are saying is that, look, if you're somehow able to guess it right for the inner as well as the outer, and together they happen to be an invariant, then you are good.
Yeah. Okay.
But yeah.
Yes, Madhukar. So I think so I need about 5 minutes just to do some administrative.
Correct. So this is all that I have. I'll upload the slides. I just wanted to remark that this is very recent work, as you can see. This is last month's paper. This is October publication, and therefore there is a lot in general that can be done, and this area has not really taken off very well, in the sense that there is still, people are still trying to do simple things, and people are still trying to solve problems at a scale where things look more manageable. So therefore,
how scalable? What is the biggest RNN that they have applied this thing successfully with some interesting invariants that they could solve? Do they say anything about that? The real benchmarks? Yeah. Okay, there is something. Yeah.
Correct. So they say that our networks are of modest sizes. So some 200 neurons, they contain an input layer of dimension 40, 1 or 2 hidden layers with 2, 4, or 8 memory units.
Okay, so the memory units are limited.
Correct. So the memory, so in their thing, the memory units are very few. First of all, it lies in only 1 or 2 hidden layers, and then also that is restricted to some 2, 4, or 8. And after that, most of these neurons come from memoryless layers. So only the first couple of layers have memory, and that also they have very few memory units. So in that sense, these are not very.
Any questions, people? Yeah, I was going to ask that people, I know we don't have the full audience today, so we should have done this. So turn your mic and video on so we could see your faces. This will be the last class for the term. So we could say goodbye after seeing your faces. I've seen some of you.
Oh, I don't have a webcam.
Okay.
Sir, may I ask, when is the model checking exam?
Oh. I thought I just asked you in the class yesterday, no? So you reminded me. So I thought it was
I forgot to ask yesterday.
December.
You also ask.
So Kapil is always very fond of asking cross-culture questions. He always asks model checking questions. No, this is enlightening. Now you could, now here it's free for all. You can ask any questions after I make the couple of announcements on everything under the sun, including politics, if you wish to. Okay, so as long as you're here, and if some of you are in Delhi, there's lots of things going on. No, so December 4th is model checking exam. So I wanted to remind you that I think we agreed on December, was it December 14th, correct?
Yeah, for
14th we had agreed for an exam.
Yeah, so for this it is December 14th, and for oh gosh, model checking? Diganta or anybody else will be?
Yeah, I think it was December 8th.
8, yeah.
I think
8. Okay, so I'll make a note right away and I will send an email. Okay, so a few things to do things on my part, okay, which I have not done, and I'll have to. Okay, there'll be an exam, and I've given a list of the topics, okay, and some people were asking for some. Just one moment. Sorry. Yeah, some sample problems. Okay, so that I will make. You know how exhaustive that list will be. I won't promise you, but I will certainly make some examples of the kind that you can expect to appear on the final exam. All that I'll do in the next by middle of next week. And I'll also assure you that you will get some of the things that you have submitted, the assignments and things graded and given back to you. I don't know if Hitat has already done that. So I will be speaking to Hitat, and that will I'll also try to get you, many of them. But of course, we need what we need for you to submit for the final project, okay? And you will get, I'll promise you that you will get a document, a one-page thing that will describe what it is that we expect as deliverables. Remember, all that, I'm assuring you that it should definitely happen before the end of next week. Now, what we have not decided yet is, Madhukar Hitat is not here, is we had asked them to give presentations, correct? So you should make yourself available during that week, 15th through 18th, okay? We will announce a schedule. So it is not mandatory that we put up a schedule. It's not mandatory. Both of you on your team should be available for the presentation. And I will also make an outline for your presentation. So, okay, what are the kinds of things that will make an outline so that you can stick to your, make your presentation comply with that guideline. Of course, within the guideline, you can make variations to fit your topic. And at least the two of you on the team should be available for your slot. But I'll keep it open. If anybody else wants to participate, they are welcome. I will publish a schedule. So these things I'll have to discuss with Madhukar and Vital before I decide. So all that information will be done. So expect those things in the next week. So we'll be in touch with you by email. And you can, if you have any questions, also send it to us. Okay. I wish I could have done all these things before today, but I've not been able to. Okay, so that was my part of the announcement. Now I'll open for any questions that you might have. Deeksha does not have a video. Deeksha, are you there? Maybe she's not there. Okay, any questions? I was just, Deeksha, I was just saying, she's chatting. Your face is not visible, but that's okay. Quite to show your face. Just to say. So if you wish to, you can turn on your video. That's all. Yeah, it's the first time we are offering this course with this application in mind. So you will get review forms in due course. So please give your feedback about what was generously give your feedback of ways to improve what you did not, what you find wanting, and so on. So hopefully we'll improve it for the next batches, and your comments will be quite helpful. Okay, so feel free to give detailed comments. I usually don't get much comments for my courses. I mean, in the sense, and I want more critical comments. Okay. So I don't mind. Anything else?
So what would be the format of the final exam? As in, would it be like a 3-hour paper? Or
Correct. As I said, it will be mostly problems, okay? And, where you will be asked to illustrate some things. Now, for example, we covered CDCL, okay? I might ask you to simulate the CDCL on an example, okay? Or I can give you a CDCL, construct the implication graph, okay? Small, I might, mostly 60 to 70% will be illustrating those concepts on the examples. Okay, that's what. Maybe 30% I might ask you to do something different. Okay, but that will require you to think. I mean, improvement to the method. Okay, or say, why is this, we talked about theory propagation, okay? Theory propagation, there are trade-offs between doing certain things, generating all theory lemmas and so on, okay? The first few questions will be some things that will test you on whether you understood what is theory propagation, okay? What's a conflict clause? What's a theory conflict clause as opposed to purely propositional conflict clause? Okay, and then we discussed certain things about, okay, if you do excessive theory propagation, it could be this thing. So some variation to the standard one that was discussed in the class. That will be for the 30% small variations to the actual algorithm. What I'm promising is that you go through your slides and go through the examples that are sample exercises that I'll send you. And if you want to supplement that, those decision procedure chapters, and in some cases, some procedures, like for example, the simplex case, there'll be a procedure, the paper. The paper is a resource. Madhukar talked about ReLUplex. There could be some simple, problems to solve in ReLUplex. We discussed inductive invariance and so on. So you can expect some simple problems on inductive invariance. Okay. So there'll be a little bit of thing to cover on all the topics that we have touched. And I usually make more problems than that is required for you to answer, so that you will have options. So so that you will at least know some core areas that if you're able to that I expect you to do. Does that answer your question?
Yeah.
Somewhat, yeah. But yeah, so I think those sample exercises will give you some idea.
Right.
Anything else?
Where do you apply? I mean, upload the list of topics that's covered in the exam.
Maybe if not, I will upload it. Right?
Okay. Okay.
I think I had. No sharing this. Yeah, this is something that we did not cover, so I can cross this thing out. Linear integer programming solver we did not cover. So verification of RNN with inductive invariance, so that I have. Yeah, this is exactly as far as I can remember. I don't know if I'll have problems on all of things, but I'll try to have at least to cover most of them. Yeah. Okay. So I will put this thing up. So look for announcements and things, uploads on the on the Moodle page. And if some things are missing there that you that you notice, please send an email. Okay, there's no further questions. I will say goodbye. Madhukar, do you want to add anything to your?
Yeah, no, yeah, nothing really. Yeah, I just wanted to say that, yeah, so this is something that the verification of RNN is something that we decided to add in the last moment. So therefore, the last couple of, this one and the last one, the presentation was kind of sketchy. Yeah, I did not get enough time to perhaps prepare it very well. The slides, the paper I had read, the slides, I did not get a lot of time to prepare. But yeah, I'll try to improve these slides, the existing one that I used today, and then upload it by the end of today.
Look, that's why in all my final exams, I usually give 30% more questions than you really need to answer, so that it'll be a smattering of things on all the topics. So even if just because you did not understand something on one particular topic should not so put you at a disadvantage. So don't worry about it. Yeah, I mean, I understand what what you were saying. So because it's the last day of class, I don't know how many people, there's only half the crowd. And of course, we are putting one advantage of COVID is we are forced to record it, and we're putting that. So yeah, so best of wishes once again for all your exams, courses, future endeavors. For as long as you're here at CMI, outside CMI, beyond CMI. And if you are interested in this area, excited enough, you want to work on something, we are both Madhukar and I. Madhukar is also looking for people to work with. I'm always open to get students, because without students, for me, students, without students, I'm nobody. Okay. Both for keeping me excited and then looking at things. That's how the brain gets triggered. So students are very important, especially if you're interested in something and that matches with our interests. So you could, that could be a very dynamic interaction. Yeah. So if you're interested in any of the things and you want to work with, even if it doesn't have to mean for your project thesis, anything else that you want, like you want to read a paper, you're excited about reading a paper, and if you want to do that, the CMI has a lot of flexibility built into its curriculum now. Yeah, I think I don't know. I mean, I enjoyed the course. I actually learned a lot because in the beginning, I was a little bit concerned when Madhukar proposed this application. And Hitarth is not here. It was good that Hitarth was able to take care of all the TensorFlow and those kinds of parts. And then you guys, some of you knew already some parts of TensorFlow and so on, because that was very important for us to have you do some hands-on and the things. In all my courses, that is one thing that you may see. I always have some hands-on. Hands-on being doing things hands-on and working with tools is something distinguishing, if you can put it, in the kind of research I do. Yeah, so I hope you got what you were looking for. And as I said, give your comments as to how we can make it better. Okay. So with that, like say bye-bye. Yeah. Until I see you next time. Bye-bye.
Bye.
See you. Thank you for the course.
Yeah, thank you.
Thank you.